guys, and welcome back to the PyTorch tutorial series. In the last video we covered the theory behind the loss functions used in PyTorch, and in this video we're going to be implementing all of the concepts that we have previously covered in the loss theory video and implemented using the Jupyter notebook. The first thing that we're going to do is to import all the necessary packages for our experiment. The first one is NumPy, and second we need to import Torch, and third we're going to introduce a new package known as NN. NN stands for the neural network package, and since we do not want to use the full torch.nn, we're going to use the nn to call all the loss functions that we're going to use in this experiment. The neural network package not only includes all the loss functions but also some other necessary neural network related modules. So let's run this cell. Now Torch has been imported and the version is 1.13.1, and we can check it by using torch.__version and another underscore. The first type of loss that we have seen in the lecture about the loss functions is regression loss. L1 loss was the simplest kind of regression loss, and it was given as the absolute value of x minus y. First, we're going to define x and y. So we mentioned x will be the predicted output and y will be the target. And in this case, we have the prediction tensor as x and the target tensor as y, just as the formula. And the shape is 2 by 3 and random numbers. Once we define the variables, then we can check the values stored in the x and y variable. Now this is going to be our prediction and this is going to be our target. First, before implementing the L1 loss from the PyTorch loss module, we're gonna do it. We're gonna use the NumPy function to convert the original tensors back to NumPy arrays and pass it into the absolute value. So we're gonna take the difference between x and y and put it under the absolute value Python function. So this is basically doing the same thing as the formula. Now we can see that the L1 loss tensor has been computed. Second, what we're going to do is to reduce this tensor and output one loss value. Most of the time we don't just want to find the difference between each element and take the absolute value. What we need is the mean of the whole tensor, and we can do it by using the reduction operation mean, and this will be our final L1 loss. So we can perform everything that we have done in the two cells by using the L1 loss function, and as an argument for the L1 loss we're going to pass x and y as arguments, so the predicted and the target values. As you can see that the L1 loss automatically computes the mean of the whole tensor. So what if we want to see the original tensor before getting the final loss? So this value is approximately equal to 1.4084, and we can just provide the parameter reduce it equal to false and pass x and y as arguments. Now when we run this cell, we might get a warning, and so this is just a warning saying that this might be deprecated. Sometimes a new version might be released, and it is saying that we can use reduction equal to none instead of reduce equal to false. So this, according to the current version of PyTorch, reduce equal to false might not work. So after some time they're going to remove this parameter and just resort to the new one. So anyways, the final output will be the same as the tensor that we got without performing the mean reduction operation. So if you don't provide any parameter here, then you're gonna get the final mean, so just a single element in your tensor. But if you put reduce equal to false, the reason we're saying reduce equal to false is that we don't want to perform the reduction operation, and it will give you the original tensor after just finding the difference between the prediction and the target, and without computing the mean. The second type of regression loss is mean squared error, and we have seen in the previous videos that it's just the difference between the prediction and the target, and instead of putting it inside an absolute value, we put it inside the square function. So we're going to define x and y again, and we're going to make them a 2x3 tensors. As you can see, our output is not a discrete value, so the targets are, since it is a regression problem, these are continuous values. That's why we're just randomly assigning the random values to x and y. So let's see x and y, the newly created x and y tensors. We're going to use the MAC loss just as before from the PyTorch module to compute the loss. But first, let's compute it manually by using the math module. So here we're gonna convert the tensors back to a NumPy array, and we're gonna find the difference between these two NumPy arrays. And finally, we're gonna take the power of 2, and here you can use double asterisks. So this is going to calculate, it's going to find the difference between each element, because it is an element-wise operation. And finally, on the output, it's going to take the square of each element. Now we get a new tensor, and we can also reduce the whole tensor and find the mean. So what we're doing is just computing the mean of all of the losses. So usually for the loss, we only need a single value, and that value is the mean of all of the losses. Next, we can do the same thing by using the PyTorch loss function MAC loss, and we provide the reduce false parameter just as before, and provide x and y as arguments. Now you can see that this tensor is very similar to this tensor, the one that we computed manually. Finally, we can compute the MAC loss and perform the mean operation in order to find the final loss value. Now we get the value of 1.9807, which is approximately equal to this value. The third type of regression loss is the Smoothie loss, and it's basically given by the piecewise defined function that we have seen in the previous video. So if the absolute value of the difference between the predicted and target values is less than 1, then we use the first equation. Notice here we're using the mean squared error for values less than 1, for deviations less than 1. But if the deviation or the difference is greater than 1, then we use the second equation, which utilizes the mean absolute error or the L1 loss. So it is a combination of the mean absolute error and the mean squared error. We're going to define the prediction and target values just as before. And now we're going to use the smooth L1 loss PyTorch loss function from the neural network module. And we're going to pass the x and y tensors as arguments. And this is going to give us a single value because we didn't pass the reduce equal to false parameter. And this final loss is computed by utilizing this equation. If you pass reduce equal to false, then you get a 2x3 tensor, which is basically computing this equation but not performing the mean operation. We can also do this manually. So in order to do that, in order to understand what is happening behind the scenes, first we can convert the tensors back to NumPy arrays and assign them to x and y. Then we're going to define a user-defined function, smooth L1 loss, which is going to be similar to the PyTorch's smooth L1 loss. And we're going to pass x and y as parameters. So we're going to utilize the equation to write the function. If the absolute value of x minus y is less than 1, which is going to be the first case, then we're going to return 0.5 multiplied by x minus y to the power of 2, which is the first equation. Else, we're going to return the absolute value of x minus y minus 0.5, which is the second equation. So this is basically the same as the equation here. And finally, we're going to create a new list, an empty list, and we're going to iterate through x up to the length of x, and we're going to create another list I, which is a temporary list, and we're going to create an inner loop, and j is going to go through the length of each row. So what it's doing is basically we're going to iterate through each row. That's what the first loop is doing, and the second loop is going to iterate through each of the rows. So it's going to iterate through each element. So we're going to append each element one by one to list I, which is going to temporarily store the rows for our outputs. And we're going to pass each element from the x and y tensors. So we're going to pass each element from the x and y tensor through the smooth L1 loss function, and the smooth L1 loss function performs this equation between x and y. And finally, we're going to append them one by one into the temporary list I. And finally, we're going to append, after each row is completed, then we're going to append it into the original list. So for the first row, we're going to compute each loss one by one between x and y. Then we're going to, when the whole row is finished, then we're going to append it to this list. Then we do the same thing for the second one, and when we are done with the second row, we're going to append it to the empty list. Then finally, we're going to convert the list into a NumPy array, and we're going to compute the mean so that it's similar to the reduce equal to false. and so that we could see the difference between the two. So I haven't defined this function first, and when we run it again, we can see that this is the original tensor, which is similar to the output from PyTorch, and the second one is after the mean is computed for this tensor, and this value is approximately equal to this value. We have finished all of the regression losses. Next, we're going to cover the classification losses. The simplest type of classification loss that we have covered in the previous video is the negative log likelihood loss. And we used this formula to compute the negative log likelihood loss. So the first thing that we can do is this prediction value, since it is a classification loss, it has to be a probability value. For regression, it doesn't matter if we use a linear output or a continuous output that is not between 0 and 1. But for classification, it is preferred that this is a probability value. So in order to convert this into a probability value, we must use either the sigmoid or SoftMax function, depending on you're using a binary or multi-class classification. So let's see the log SoftMax function from the neural network module. We're going to create a new tensor, and its shape is 2x4. So we have 2 rows and 4 columns. Next, we're gonna pass this x into a new function known as log SoftMax. Remember that this is a functional module, so the first thing that you need to remember is the thing that you're passing inside the first parentheses is going to be a parameter to the function itself, and the second one is similar to what we're doing when we are creating models. If you're familiar with Keras, using the functional API, you can build upon models, and you can pass the previous layer onto the next layer by using a second parentheses. So remember that don't put the x inside the first parentheses. So any input to the function must be provided on a different parentheses. We're providing dim equal to 1 as parameter because we want to perform the log SoftMax function here on the first axis. So we're going to be performing it across the rows. So let's see what the output will be. So currently it's applying the SoftMax function on each of the values, and then after performing the SoftMax function, then we get the y. Now it's a probability value. Then what it's doing is performing the logarithm function on top of the SoftMax function. So the output that we're getting is after performing the log and the SoftMax on the prediction tensors. So we can consider what this is doing by computing it manually. So first we can convert our original tensor to a NumPy array. Then we create an empty list. Then we create a loop which is going to iterate on each row. Then first we must apply the SoftMax function, and the SoftMax function is given by the formula here. This is the SoftMax function. So we have to pass each prediction onto the exponential function and divide by the summation of the exponential function for each prediction, and we're going to sum them together. So here what we're doing is first we have to compute the softmax, so the exponential function, and each prediction by indexing k is going to iterate through each element, and it's going to pass them onto the exponential function. Then it's going to divide them and by the sum of after passing each prediction onto the exponential function. So this is the denominator and this is the numerator. Then after computing the softmax function, then we pass it on to the log function again. Notice that we're using the NumPy module to use the log and exponential functions. Finally, when we print out the list, we can see that these values are approximately equal to the one that's given by PyTorch's log softmax function. So all of this is just computing the log of the y. So we haven't computed the loss yet, so the negative log likelihood loss is going to be computed by first creating a prediction tensor. Now we're using a 3x4 tensor. Then we have already covered the log softmax function from here, and we're going to pass x0 onto the log softmax function. So this is original tensor x0, and this is the output after performing the log softmax function. Next, we need target variables. So these are going to be our targets, and it's going to be long numbers. Long tensor creates long integers, and we need 3 elements. And the random part is just we pass a seed. This is called a seed, and you pass a seed, just a random number is enough. Depending on what type of number you enter, if you want to regenerate the same output, then you have to provide the same seed number. If I change this number, I'm going to get a different output. Now, the negative log likelihood loss can be used from the neural network module, and we're going to pass our prediction, and these are the targets. Notice that the targets are not one-hot encoded, and these are just labels, class labels. You might consider them as class labels, and each of them are going to pick which loss is going to be preferred. So index 1 means if this is index 0, then I prefer index 1. So each row is going to be considered as one prediction, and these numbers indexes are going to tell us which loss to pick from each row. Next, when we pass x and y to the negative log likelihood loss, then it's going to compute the negative log of x, so the entire thing. And when we put the reduce equal to false, then this is going to compute the mean after performing the negative log likelihood for each prediction. So this is similar to what we have done before, but here it's going to give us an output of a single output and a number, and this is going to give us a tensor instead of a number. So we can compute the loss manually in order to understand what the negative log likelihood loss is doing under the hood. So we can convert x and y back to numpy arrays. Then we can create an empty list, and we can iterate through each row of x for the predictions. Then finally, as I mentioned before, this part yk is just using the indexes. So y0 is 1, and y1 is 0, and y2 is 3. And we're going to use this as an index into x. So xk is going to pick the row. So k equal to 0 will be the first row, k equal to 1 will be the second row, and so on. And we're using another square brackets, and we're putting the elements inside y as an index to, as a second index to x. So now we're accessing each element for each row. So for the first row, since we are accessing the first element, then we're going to pick index 1. So instead of this tensor, it will be this tensor, and we will pick this as the first loss. For the second one, we will pick index 0, so we will pick this second loss. And for the third one, we have to pick index 3, so we will pick 0, 1, 2, and 3. Then finally, once we append all of the losses which are selected, which are this one, the first one, and the last one, then we're going to append them to a new list, and this will be the output from our negative log likelihood loss without performing the mean. And in order to get the final loss, we don't have to provide the reduce equal to false, and this gives us a single number. This is similar to finding the mean of this tensor. Finally, we can check if these two values are similar, and you can see that these values mirror one another, and the final loss value is approximately equal to this value. Notice that all of these values were negative because the negative sign was not applied after computing the log SoftMax, because it's just performing only this operation. But once you pass it through the negative log likelihood loss, we're adding a negative, and all of these values are going to be positive. And these values are selected by using the target indexes. The second type of classification loss that we have covered is a binary cross entropy loss. And for the binary cross entropy loss, we used this equation. So it's used for binary classification, so we only have two classes, either 0 or 1. So if we have 0 then as a class label, then this part will be gone and we only use this equation. And if we have the class as 1, then we don't have the second part and we only use the first equation, which are both kind of similar to the negative log likelihood loss. Remember that the first one has multiple predictions, more than one prediction. So we were using the SoftMax function. But for binary cross entropy loss, since we only have two predictions, then we have to use the sigmoid function instead of SoftMax. That's why we're going to replace the log SoftMax function here. Remember that PyTorch also has a function known as SoftMax, and it has another function known as log SoftMax. So if you use log SoftMax, it's going to apply the logarithm after the SoftMax operation. But in this case, we're just going to apply the sigmoid function on the prediction first and save it to y. And we're going to create a 2x4 tensor. So x was originally a 2x4 tensor, and we're going to pass x into the sigmoid function and assign it to y, and we can print out y. Notice that each of the values are between 0 and 1, but previously they weren't. Now we can convert x back into a numpy array from a tensor into a numpy array and manually compute the sigmoid operation by ourselves. Remember that the sigmoid function is 1 over 1 plus e to the power of minus x, so we have to use this formula so that it could give us the same output as the sigmoid function being deployed by PyTorch. So we're going to use a user-defined sigmoid function and pass the original x as a numpy array. Then we're going to use 1 divided by, for the denominator we have 1 plus, we have to use the exponential function, and minus x, which is similar to the formula. Then when we pass x into the user-defined sigmoid function, then y will be, we haven't defined the function first, and here we need a colon. Now everything seems to be fine, and here we have the y tensor after the sigmoid operation. So this value is similar to this one. Now for binary cross entropy loss, we're going to use a single label first, and second we're going to use multi-label. We have covered the difference between a single label and multi-label in the previous video. Single label means you have one label for one training example, and multi-label means you have multiple labels for a single example. So let's create another tensor which is a random number and which contains 3 elements, and we're going to pass it through a sigmoid layer just as we did before. We have covered this extensively so that you understand the sigmoid function first. Then we're going to assign it to x. Finally, when we print x, it's also going to be a tensor containing 3 elements, and all of these values are going to be between 0 and 1 because it's a sigmoid layer. Next, we're going to define our target variable, and it's going to be a float containing 3 elements, and we're going to provide a random seed of 2. Notice that our target variable is now containing 1s. Now, if you want to calculate the binary cross entropy loss between x and y, then you have to use the BCE loss from the neural network module. Then when you print out this one, then you get a final loss value, which is going to compute the mean of each of the losses after using this formula. And the second one, if you put the reduce equal to false parameter, then it's going to give you a tensor with 3 elements without performing the mean operation. Now let's see what's happening behind the scene for the BCE loss. So the first thing that we can do is here we're defining a new function loss, and we're assigning it the BCE loss, and we're providing a parameter known as size average is equal to false. Then this loss can be assigned to a variable, and you can use this variable, you can call this variable as a function and pass the x and y as arguments. So as we proceed to the next section, you're not going to be if you're not using Jupyter Notebook, then you have to assign this loss function first to a variable, and then this variable can be called as a function because it's an instance of a class, and you can pass x and y to the loss function. So this is basically doing the same thing as passing the x and y originally to the BCE loss. We did this before because it can be printed so that we could see the output directly. Once you assign this to another variable, then when you print out the loss, it's going to give you 2.1686. Here it's giving you a warning saying the size average and reduce arguments will be deprecated. Please use reduction equal to sum instead. So we have used the size average and reduce parameters, which are now deprecated. So size average is just reduction equal to sum. Instead of the mean, we're just summing up and outputting the final loss value. So here we have three methods that we have covered in order to get the final loss. Now we can use manual implementation to see what BCE loss is doing under the hood. First, we're going to convert each tensor back to a NumPy array by calling the .numpy method on both. Then we're going to create an empty list, and we're going to iterate through each element. Finally, we're going to find the negative log likelihood of each of the elements, and if it is equal to 1, we're going to use this one, because if the target variable is 1, then if the target variable is 1, then this part will be 0, and we only have this one. We have 1 here, so the only thing remaining will be the log. That's why we're using np log of xi here. Else, which means y will be 0. Here we don't have 0 in this case, but if it is 0, then we're gonna use 0 here, and finally this term will be gone, and the only term remaining will be the 1 minus h of x. So this is the same thing as the negative log of 1 minus xi. Then finally we can print out the list and compute the mean, and these values are similar to the original outputs. So this is a final loss value after performing the mean, and this is a tensor which is equal to the BCE loss computed by passing reduce equal to false. We can also perform another extra operation. Instead of using the if-else here, you can use the entire formula, and you can multiply the yi and the 1 minus xi here. So this is basically doing the same thing as the formula. And you get the same output. So this is for a single label case, but what if we have multiple labels? So for a multi-label, we're going to define another x prediction, which is going to be 3 by 2, and we're going to pass this x0 into a sigmoid layer again, and we have our final predictions, which is a 3 by 2. Notice that we have multi-label. That's why we have 2 labels instead of 1. The original was a single array. We only have 1 prediction here for each case and 1 target. But for this one, we have 2 predictions, and we're going to have 2 labels, and the labels are also going to have the same size, and it's going to be 1 1 0 0 and 1 0. What it's saying is we have multiple labels being presented at the same time. So here we have both labels indicated as 1. Here we don't have both labels, and for the final one we have the first one as 1 and the second one as 0. So here it's kind of similar to just having the 1. We're going to do the same thing and compute the BCE loss between x and y. Then the BCE loss will be 0.85. And if you provide the parameter reduce equal to false, then you're going to have a tensor without performing the mean of this tensor. So in order to understand what is happening for a multi-label binary cross-entropy loss, we can convert x and y back to a NumPy array first. Then we're going to define an empty list. Then we're going to iterate through each row after computing the sigmoid layer. Then we're going to iterate through each element in each row. That's what the second loop is doing. And we're going to create a temporary empty list to store each row, and once each row is done, and we're going to append it to the original list to create the final tensor. So in order to get the elements, we also use the same kind of computation that we used for the first case, but here, instead of having just a single index, we have to use double index. So if yij is equal to 1, so for example, let's say for the first row and first column, which means 1 1 is 0 0 is this one, 0 0 and 0's column. So if it is 1, then use the negative log likelihood xij. So pass the value from xij, which is x00 will be this one with the corresponding element, and we're gonna pass it into the logarithm and compute the loss, the negative loss value. Notice that x is has already passed through the sigmoid, so the only thing we need to apply is the logarithm. But if it is 0, for the case, for example, for this one, which is row 1, index 1, and column index 0, then the corresponding loss will be this one. So if it is 0, then we use this formula. Instead of using this one, we have to use 1 minus this one. Finally, after computing each row, we're going to append it to the final list, and we can see the final result. And this is going to be similar to the one computed using PyTorch. Equivalently, we can use the entire formula instead of the if-else statement to compute. Notice here we're using a single index because Elementwise operation can be carried out by even NumPy. So for the if-else, we need access to each element, but here we're just using a single loop. That means we can do it for the entire row at once. So we can do this operation for each row. And the result is going to be the same. Next, we have seen the difference between the BCE loss and the BCE Lotus loss. So, as a reminder, I mentioned that if you use the BCE loss from PyTorch, it's not going to guarantee that the prediction values are going to be converted between a value that's between 0 and 1. So that's why we pass the x through a sigmoid layer first before passing it into the BCE loss. But in the case of a BCE with Lotus loss, this is just simply adding a sigmoid in front of the BCE loss above. So let's see BCE with Lotus loss for a single and multi-label. So let's create x first and pass x through a sigmoid layer. And all values will be between 0 and 1. Let's create our target variable. All of them are 0 in this case. First, let's use the BCE loss and pass the x which has already passed through the sigmoid layer, and we get a final loss of 0.69. And let's use the BCE with Lotus loss and pass x instead of xs. Notice that xs already implemented the sigmoid, but I have already mentioned that BCE with Lotus loss already has sigmoid under the hood, so we don't need this to be passed as an argument, but we need to pass the original x without a sigmoid as a parameter. And notice that these two losses are the same. So it's basically showing you that BCE with Lotus loss does the same thing without implementing the sigmoid layer first. So this is the case for a single label because we have single targets and single predictions. For the case of multi-label, we can have a 3x2 tensor and we can pass them through the sigmoid to convert them between 0 and 1. And finally, we can create a 3x2 multi-label tensor, and we can pass xs to the BCE loss, and we can pass the original x to the BCE with Lotus loss, and we get the same result. The final type of classification loss is the cross-entropy loss, and it's given by this formula. We're going to create a prediction tensor of 2x4, and our target is going to contain two long integers, and we provide a random seed of 4. When we print out x, it's going to be a 2x4 tensor, and when we print out y, it's going to contain only 2 elements. So the cross-entropy loss is basically the same as the binary cross-entropy loss, but this general loss function can be used for general purpose or for when you have multiple classes and not only 2 classes. So if you put reduce equal to false, that means you're gonna get the whole tensor as an output, and if you don't pass the argument, then you're gonna get the final loss after finding the mean. So this will be the final cross-entropy loss, and this will be the tensor. Here we have the sigmoid. So let's try to understand what is happening when we call the cross-entropy loss method. First, we need to convert x and y back to a numpy array again, and we're going to define an empty list. So for k in the range of length of x, so we're going through each row. Then we're going to compute the sigmoid, the softmax function first. So the softmax function is, so xk, for example, for the first row, we're going to select elements based on the index we get here. So here we're going to select the first loss because the target is 0. And for the second one, we're also selecting the first one since the target is 0, because we're passing yk as the column index for x, and the row index will be k. Then at the bottom, we just find the we pass xk, the entire row, into the exponential function. Then it's going to perform the exponential of each of the elements for each row by using Elementwise operation. So it's going to find the exponential of each element, since we are passing the entire row into the exponential function. And when we take the sum, it's going to take the sum of the entire array. Then this will be the denominator part, and this will be the numerator. And finally, we pass the result from the softmax into the logarithm and add the negative sign and append it to the list. So the output tensor is also similar to the one that we get for the cross-entropy loss, and the single output is similar to the results that we get from the cross-entropy loss without performing the mean. So notice it's using this formula to compute the cross-entropy loss, and each y is being passed through a softmax because it's a cross-entropy loss is being used for multi-class problems. Then we apply the logarithm and the negative sign. Finally, when we take the mean, then we take the summation and divide it by the number of elements to get the final loss. That's all for losses, and starting from the next video, we're gonna see the theory behind optimizers and implement them using Jupyter Notebook.
Audio Jungle.